So the next method is effectiveness NTU method. In this case, we do know the surface area of the heat exchanger, but we don't know the outlet temperatures. So our goal is to find outlet temperatures and also find the heat transfer rate that can be achieved with this heat exchanger. So let's start with the definitions. So in this case, we define a term called effectiveness. So it's called heat transfer effectiveness. It is defined as the actual heat transfer rate divided by the maximum possible heat transfer rate. So now I'm going to describe in a moment what is the maximum possible heat transfer rate. So the actual heat transfer rate, Q, is simply mCp delta T, mCp delta T, so for the cold side and for the hot side. So we can combine this m times Cp as capital C. So this is the product of mass flow rate and Cp. So let's call this as the capital C. Okay? So capital C for the cold side, capital C for the hot side, and Q is equal to basically delta T for the cold side or delta T for the hot side. Okay? Q max is defined as the minimum of the Cp, C cold versus C hot. So you compare the capital C cold, capital C hot, and whichever is minimum, you use that one and multiply it by delta T hot in minus delta T cold in. So this is the maximum temperature difference. Okay? So C min is the smaller of these two quantity, and this is T hot in minus T cold in. So the effectiveness is defined as Q over Q max. Q, we can take it either for the cold side or hot side, for the hot side or for the cold side, but Q max is the same. So you can calculate effectiveness either way, so from either hot side or from the cold side. So this is the definition of effectiveness. NTU, which means the number of transfer units, is equal to U times AS divided by C min. Okay? C min, we just define it here. Number of transfer unit is U times AS, and C min again Cp times M min. Okay? So now we define epsilon and we define NTU. So the approach is as follows. So we calculate T max, T hot in minus T cold in. You calculate C min, you calculate Q max, and then you calculate NTU because we have we know the area, we don't know outlet temperatures, and NTU is only function of area and C min. So based on NTU and epsilon, so based on NTU and C min over C max, you calculate epsilon. So there are graphs and there are equations that will allow us to calculate epsilon. So NTU we calculate based on the area and overall heat transfer coefficient. C min and C max we compare and we determine. So then we calculate epsilon from graphs or equations. So now, and I remember the definition of epsilon is Q over Q max. And Q max I can calculate from here. Epsilon I read it from the graph or from an equation. So then I can calculate, if I know these two, I can calculate Q actual. So if I know the Q actual, so that is Cp, T cold out minus T cold in, C hot, T hot in minus T hot out. So that means after I know this, I can calculate the outlet temperature. So that is the approach. So again, so I mentioned epsilon can be calculated from the equations. So we have these equations here. Everything is written in terms of C min over C max, which is the capacity ratio. So everything is function of NTU and CR, capacity ratio. So if you know NTU, if you know CR, you just check the geometry, parallel flow, counter flow, shell and tube, cross flow, all heat exchangers. So you should be able to basically read it or pick your equation based on the flow arrangement. So again, we have parallel flow, counter flow, shell and tube, one shell pass, n shell passes, cross flow, mixed and unmixed, and when the CR is equal to 0, which means phase change, you have all the equations that are the same for all cases. Okay, so this, when the capacity ratio is 0, so that means Cmax goes to infinity, the phase change, all the flow geometries have the same equation. So you also have, if you don't like to use equations, you also have graphs, so you can read. So you read your NTU value, which is in x-axis. X-axis is your NTU value. And you have different curves for different Cmin over CR, Cmax. So this is the capacity ratio. So you basically read your NTU and find the curve that corresponds to your capacity ratio and find the effectiveness. This is for parallel flow. So we have a similar curve for counter flow. We have shell and tube heat exchanger, one shell pass, two shell passes. So the idea is always the same. You find the NTU in x-axis, find the curve for CR, and read the effectiveness. And we have cross flow, both fluids unmixed. One is mixed, the other is unmixed. And again, everything is also given in here, these equations. So if you don't like to read from the figures, you can use the equations. That is maybe more accurate. And if you want to just compare parallel flow and cross flow, let's say the capacity ratio is 1 for both of them. Okay, the capacity ratio is 1 for both of them. So the parallel flow, as you can see, the least effective. Counter flow is the most effective for a given area. So the cross flow is in between. So this is very important. So based on this analysis, the most effective flow is the counter flow. Parallel flow is the least effective one, and cross flow is in between these two.